everybody. This is the second video on sketching parametric equations and what they are, okay? So we're going to start by taking a look at an example over here, excuse me. But here's what I want to start with saying. When we talk about sketching parametric equations or equations that are in which x and y are defined with respect to a parameter or an independent parameter variable, we call these curves in a plane, of course, a plane curve, but I think it's very important that we get the vocabulary down here. But we say we're sketching plane curves. And let's just start by looking at what we've got over here. Okay, so we say x is equal to t squared minus 4 and y is equal to t over 2, where t is our parametric variable or our parameter, okay? But what I want you to recall is really what this does is we're letting t be the independent variable here and just kind of wander. And what that does is it generates a set of different points or coordinate pairs, x, y, with respect to a t value, okay? So what we should probably start by doing here is we'll define a domain, if you will, okay? And really what we're doing is we're restricting t so that we don't have to graph the entire graph. But let's take a look at what we've got here, okay? And we'll start by drawing in or sketching in a table, okay? But the important thing here is this, just again, this realization that what we're doing here is necessarily letting t be the independent variable and letting both x and y depend upon t at the same time, okay? So what we'll do is we'll just kind of, for the sake of this example here, we define the domain of t as being from -2 out to positive 3. But let's go ahead and take a look at this, okay? So what we'll start by doing is filling out all the values for x. And we say, so x was represented or defined as being t squared minus 4. So we've got, in this case, -2 squared, which is 4, minus 4, which would give us an x value of 0. Moving on, -1 squared is 1. 1 minus 4 is -3. 0, we got here 0 plugged in would just eliminate this t squared term, and we have -4. And the neat thing about this is once we plug in 1, we'll have 1 squared is 1, minus 4 is -3. And you'll see that this is kind of like it's quadratic motion or quadratic function-ish. Of course, we have t squared minus 4, but 3 squared now minus 4 is 9, minus 4 is 5, okay? So now we've got all the x components to all of our solution points for these parametric equations or equations defined with the parameter t. But let's go ahead and go look at y here. And y is going to be a little bit more simplistic but because it's just linear. But we say t over 2. We say, okay, so since t was -2, we got -2 over +2 is going to give us a y value of -1. Moving right along, we say, okay, so now let's plug in -1 for t. -1 over 2 is, of course, -1/2. 0 in for t is simply going to cause this to be 0. 1 in for t is going to be y value +1/2. 2 in for t, we've got 2 over 2 is 1, of course, and then 3 over 2 is 1/2, or just we'll say 3/2. Now that we've got this, really what we're doing is we're going to focus on this. Although this column is the reason why we were doing this. And if you recall from the last video, I brought up the fact that with these plane curves, we're graphing them with an independent variable t being, you know, what x and y both depend upon. But we typically use t to represent time. And so what this is really doing is giving a good idea of the position of maybe a projectile at a given time. Or we let t wander in seconds. But let's go ahead and kind of sketch this curve right here and point a few things out about it. Okay. The first thing I want to point out is this. We do not alter the x-axis to represent t. We let x be x and y be y. And another thing I want to point out is this. You notice that we define the domain of t as being from -2 out to 3 inclusive, but the fact of the matter is this. When we made the table, we started with an x or t value, excuse me, of -2, and you know I chose to go up by 1 every time for my scale. It doesn't matter if your scale, but what your scale is. But this going up right here presents us with a new set of x, y every time. And the important thing is this, as we graph these, this parametric equation is going to assume a direction. And that direction is what we typically refer to as the orientation of the plane curve, okay? So, you know what, you'll see me graph this here, and you know, I might draw in a few arrows just to show you what I'm talking about here. But we say, okay, so the first point here was 0, -1. So we've got x is 0, y is -1. Go down here and draw a dot. The next now x and y value produced by the next higher t value, or this always goes in increasing order here, but was -3, ½ So we'll go ahead and proceed back 3, and we'll go down 1/2, and that's right here, okay? The fact of the matter is if we were to start tracing this right now, I would go ahead and put arrows on going this way because my curve is proceeding in this fashion, okay? The next point here we have an x value of -4, a y value of 0. So -4 is 0. -3, comma half, so back 3 up a half here. And all the while just kind of proceeding in this direction. So I'll just keep putting some arrows here for our orientation. We say, okay, so that was -3, comma half, 0, 1 is here. Just kind of trace that in there and draw in our arrow, and then 5, comma 3 halves. So 1, 2, 3, 4, 5. So you can see this graph really kind of picks up here at the end. So it's speeding up, or covering more, if you will, distance over a given time parameter t that's proceeding in a linear fashion. But you can see that the orientation of this curve is starts to the left, going up and increasing y values, and then proceeds to the right. And that would be our parametric equation defined by these parameters, or this parameter t over here.